fill these S boxes. Only the input bits which are falling, and we can try to linearize only those S boxes which are concerned. Yeah, for those unrelated S boxes, we just ignore. Yeah? So in that method, we can actually do linearization of the S boxes concerned in Chi0 only. And this will save us some degree of freedom, and we can actually do 2 rounds linearization for that. Just for example, the color doesn't show here. It's okay. Just for example, if we have a S box which have a requirement on B0 and B1, means we only need these 2 bits of a S box output to be linear. The rest 3 we don't care. Okay, how can we achieve that using minimum linearization? To ensure both B1 and B0 to be linear, we can simply fix A2 to be 0. If we fix A2 to be 0, you can see B0 becomes A0, which is linear. B1 becomes A1 plus A3, which is also linear. So by fixing 1 bit, you get 2 bits to be linear. And that's it. Yeah? So we save a little bit more. So previously, to fully linearize a S box, we need to fix 3 bits of a S box. However, since only B1, B2 are concerned in this case, we just need to fix 1 bit. So we save a little bit more in this case. So to summarize, if the S box, so we divide the cases into active and non-active. So active means there's some difference passing through the S box, and non-active, there's no difference in the S box. For non-active cases, we can actually save quite a lot when there's only 1 bit in concern. Yeah, we actually save. Sorry, when there's no bits in concern means you don't really care about the S box, so you don't need to linearize it. When there's all 5 bits need to be linear, then you don't save anything. When there's only 1 bit in concern, you can set up a 1 bit equation only, so you save 2. For other cases, you can save 1. Yeah. For active S boxes, depending on the mask, for the first 2 cases, there's no degree of freedom saved. But for the 3rd case, there's a degree of freedom 1 saved. Yeah? So in both cases of active and non-active S boxes, there are some degree of freedom saved. So that's how we do 2-round connector. And then to use this one, we first need to find out a very high probability differential, fulfilling the condition that the output D bits, first D bits are 0. And here we have also some extra constraint that it consumes as less possible degree of freedom as possible, because the connector can provide very limited degree of freedoms. Yeah? And we do this on a GPU implementation. So usual CPU implementation can evaluate roughly 2 to the 21 Ketchuk evaluations per second. But on a GPU, very low-end game-used GPU, we can actually evaluate up to 2 to the 28 or 2 to the 29 evaluations. That's quite a significant speed up. Actually, that's about 100 to 200 times speed up evaluation. compared with CPUs. And this enables us a computation power up to 2 to the 50. Yeah? So using this method, we can actually attack up to 6 rounds of the Kerchak collision out of 24. Yeah? And again, the Kerchak designers have proposed that this context to avoid those batch attacks against collision with lower security margin with capacity set to be 160. And we did for 6 rounds for the best cases. And for distinguisher, the most effective distinguisher is zero sum. Yeah? For zero sum, it means that find a subspace of the input so that the sum of the inputs is 0. In the meantime, the sum of the outputs are also 0. This is what we call zero-sum distinguisher. Yeah? And intuitively, we can have zero-sum if the dimension of the function is given. It's just like a differentiation. Yeah? If you have a degree f, we try the differentiation for degree f plus 1, you will get 0. Yeah? And the attack works in this way. We start with a linear structure and we go forwards n rounds and backwards m rounds. We try to limit the edge break degree in this portion and this portion so that we can ensure the inputs and outputs sums to be 0. So recall that for forward round, the chi is of edge break degree 2 and the chi inverse edge break degree 3. So for n rounds forward, the edge break degree is 2 to the power of n. So backwards, m rounds, the edge break degree is 3 to the power of m. So if we have a linear structure of size twice of this maximum of 2 to the n and 3 to the power of m, we can ensure that the sum of the inputs and outputs are both 0. So the attack heavily depends on how many rounds we can have here. What is the maximum degree of freedom the linear structure can provide? Yeah? So of course we want T to be as large as possible and the size of the linear structure to be as large as possible. And here is the 2-round linear structure of dimension 512. Yeah? So same as before, we limit the sum of these 2 columns to 0 and you can check the outputs is linear. If you invert this state by 1 round, it's also linear. Yeah? So that's how we have 2 rounds. 3 rounds, linear structure is for dimension up to 194. So you can see with the sum of these 2 columns to be 0, the first rounds will be linear. So if we trace the propagation of the variables in the second round, you can see there are no neighboring variables in each row. So the output of the chi is also linear. And the initial state here can be inverted by 1 round as well, while keeping all the variables to be linear. Yeah? So that's how we get 3 rounds and dimension 194. So the dimension 194 comes with the constraint that for this 2 columns, we have to ensure is 0. And for each column here, because this is the second round, theta is here. So for each column here, we need to ensure the sum is 0 as well. Yeah? So 2 bits constraint, 5 bits constraint. So in total, you have 7 bits constraints for, in total, 10 bits variables. So you are left with 3 bits. And each line has 64 bits. So in total, 192. But how do we get 194? Because we notice there are 2 bits are dependent. Yeah? So that's how we do distinguisher. For the middle, we follow the linear structure, either 2 rounds or 3, depending on the size of the linear structure needed. And for this backwards and forward rounds, we try to see what is the maximum edge break degree for each direction. And the complexity is simply the maximum degree plus 1. Yeah? For example, 198. The complexity is 2 to the 129. So in this attack, we can actually do up to 15 rounds, yeah? Out of 24. The last attack is key recovery. It's used in some keyed constructions. So this is one of them. This is KMAC. So instead of processing the message alone, you actually process some nonce and sorts followed by the key, followed by the message. Okay. So before the message, you'll get the key. So everything will be keyed after it. Yeah. And there are also other constructions for authenticated encryption called KYAC and KJ. It's keyed in similar ways. Instead of keying the first R bits, actually here key is inserted to the whole state, and here as well. Yeah, so that's the difference. So in key recovery attack, what we do is roughly the same. Cube attack, we try to calculate the linear edge break degree of the rounds we attack and come up with a linear structure where the size provided by this linear structure is higher than the edge break degree of the remaining rounds we are attacking. So if we can ensure that, then we know that the sum of the outputs are 0. And whether this sum is 0 depends on the values of some key bits. Okay. So in other words, if some of the key bits are 0 or 1, it will affect the result whether the output sum will be 0 or not. So depending on this information we can recover the key, yeah, by checking whether the output sum is 0 or not. And there are many methods to extend this initial few rounds to more rounds, and to find linear structures with higher dimensions. And the results are, for KMAC, which is the official message authentication code by NIST, we can attack up to 7 or 9 rounds out of 24. For KCHAC-MAC, we can attack up to 7 rounds. And for KYAC and KJ, these are the submissions to the CISA competition. We can attack up to 9 rounds out of 14. Yeah. The last construction is called cravat. This is a construction of a pseudo-random number generator out of the round functions of SHA-3. Yeah? So basically there are 4 permutations, PC, PD, and PE. All of them are based on SHA-3, either 4 rounds or 6. Okay? So it starts with a key, pad it, generates a key in, which masks the input, and another key, K out, masks the output. Yeah? So at each layer, you have a message block masked by the K in, pass through the permutation PC. If you do this for all message block, sum together, pass through the permutation PD, and we split into 2 to the L layers again, and there's a rolling function, change the states into another value, pass through another permutation, XOR the output mask K out before outputting the random number 0. Z0. Yeah? So all the permutations, PP, PC, PD, PE are being 4 or 6 rounds, K-check P. Yeah? And this can be attacked by meets in the middle and the linear recurrence attack due to the low algebraic degree. Yeah? Just imagine if you get 4 rounds here and 4 rounds here, in total, 4 plus 4, you get 8 rounds. 8 rounds, if you split into 7 plus 1, for 7 rounds, the algebraic degree is 128. If you can come up with a linear structure of size a bit more than that, you are able to see a zero sum in the output. Okay? So how do we generate the linear structure? You notice this is a sum. Yeah, this is a sum. If you have a message here and take another message, M0, change it to M0 prime, let's say, you will have 2 different values here. Similarly, if you have M1 and M1 prime, you have 2 different values here. You do the same for all the layers. Since this is a sum, you get a affine subspace of dimension 1 here, affine subspace of dimension 1 for each line. So you get L lines. So in total, you get 2 to the L of dimension affine subspace after the XOR. Yeah? Yeah? So if the L is bigger than 128, we are done. Yeah? So that's what you can choose. So you can get a very big affine subspace after the XOR. And then for this 4 round and this 4 rounds, as I said, we can split into 7 plus 1. 7 rounds, algebraic degree is 2 to the 128. And for the extra rounds, you can actually do the invert, yeah? As we have done before, inverting the chi. Yeah? So actually, you can observe a zero sum after 7 rounds. And you can check whether this is consistent by using the output there and inverting by 1 round. So in this way, you can actually attack this construction and recover the key. So this is not a secure construction, actually. So in conclusion, 5 or 4 rounds of SHA-3 can be attacked with respect to collision and preimage resistance out of 24 rounds. So you can see there are still huge security margin left. Yeah? For example, for SHA-2, there are in total 64 rounds. The best attack can attack up to 50 rounds, something around that. So means 80% can be attacked. However, in case of SHA-3, 20% only. Okay, so you get a security margin of 80%. However, for key recovery attacks, we can attack a bit more, like 9 rounds. So if you decide to make use of the reduced version of a SHA-3 in the keyed version, you should be very careful. Yeah. Okay. That's the talk. Thank you. Do you have any question?